Welcome to today's Copernicus Data Space Ecosystem webinar, where we'll be exploring how to gain valuable insights from Sentinel imagery using the Sentinel Hub Statistical API. In this session, William Ray will walk you through the API's core capabilities, show you how to build your own statistical API requests, explain how Evalscripts integrate with the API, and he will demonstrate curated examples from the notebook samples repository in the CDSE Jupyter Lab. Will has been an education solutions engineer at Sinergise for over 4 years now, and he's helping users to unlock the full potential of our observation data. His expertise with the Sentinel Hub APIs makes him the perfect guide for today's topic. So without further ado, Will, the stage is yours.
Great. Thank you very much, Sabina. Okay, hi everyone. Really excited to be here to talk about the Sentinel Hub Stat API, part of the Sentinel Hub APIs in CDSE. So today I'm going to introduce you to what the API is, how it works, why you might want to use it, and then I'm going to run through some examples to show you how you can very quickly gain some insights into your satellite imagery, including either Sentinel-1, Sentinel-2, Sentinel-3, or your own data if you so wish. So without further ado, let's get into it. Okay, so the statistical API calculates statistics from your EO data, and what its key selling point is that you do not have to download the imagery itself. So in the past, if you wanted to generate, say, the mean NDVI for a field of interest, you would have to download your Sentinel-2 image. You'd then have to clip your bands, your area of interest to a single field, then calculate the mean NDVI, which is quite a long-winded, inefficient process. With Stat API, we've really streamlined this so that it's a much more scalable solution. So in a request, you specify an area of interest, a time period, an eval script, and whichever statistical measures you wish to calculate. So examples of this, you might want to calculate the percentage of cloudy pixels for a given area of interest and time period. You may wish to look at the mean, the standard deviation, and a histogram of band values for a specific band or spectral index, and many more visualizations. So I'll show some really cool examples at the end, which you'll then be able to go implement for yourself. So maybe you think I've never used Stat API before, but even if you're just a beginner user who's been using Copernicus browser, you will have been using the Stat API in the background. So I've got 3 good examples here for you. Firstly, the Spectral Explorer function in Copernicus browser. This enables you to generate spectral plots for a given area of interest. So here we have a little field on the left, and we can actually compare it to some common land cover types. So our area of interest is the light green line here. I've plotted also on here grass, soil, and you can see that it's definitely not soil, but actually its curve is quite similar to grass. Like, it's not quite as bright, but it's a very similar kind of profile. And this allows us to start kind of guessing what the land cover type might be. In addition, you can generate histograms in Copernicus browser. Here's our same field again, except here we're looking at NDVI. And you can see that the peak NDVI values are all clustered above 0.8, which to me indicates that it's a very highly productive field. You can also perform some multi-temporal analysis in Copernicus browser. So here we're looking at a time series for this field of interest. We're looking back from the start of the growing season in March all the way up to August this year. And you can see here that the NDVI values are kind of low most of the growing period up to probably about May. And then you can see a big jump And that obviously indicates that's probably when the crop may have been planted or started to germinate. Yeah, so that's the kind of basic tools you have in Copernicus browser. So let's actually have a look at some API requests. So here is a super basic one for us to look at. We can start right at the top. You can see here that we have our inputs. The first of these is a bounding box in this instance. We can see the projection we're using, 32633. We then define in our data input the data collection. Here we're using Sentinel-2 level 2A data collection. And we have a mosaicing order as well. So we're using least recent. But like processing API, you could specify this as the least CC, so the least cloudy, or the most recent image. That's up to you. We also have a time range parameter coming in. So here we're looking at data from the 4th of July to the 5th of July. So quite a specific time range. And you can also see we have this input called an aggregation interval. So for those not familiar with the API, this is a new input parameter for you, and we're going to go in a little bit more detail about that later. And then lastly, we define our Evalscript, just as we do in processing API. We'll take a look at that in more detail in a bit. And then a resolution. So because we're using Sentinel-2, naturally our resolution is going to be 10 by 10 meter pixels. So yeah, let's go back to this aggregation interval. And we're going to examine how Stat API splits your time range into multiple time periods. So in a single request, you can actually retrieve data from several dates at one point at the same time. And this is defined through your aggregation interval. So in this little example here, we've got a time range from the 1st of June 2020 to the 31st of July 2020. And we've set an aggregation interval of P10D, which refers to the number of days. So in this instance, what we want to do is retrieve one data point every 10 days. An aggregation interval has to be at least 1 day long, but it doesn't need to fit perfectly in your time range. So the API will automatically slice your aggregated time periods up. So yeah, as written here below, if the time range is not divisible by the aggregation interval, by default, the last slice or time interval is dismissed. But you do have the option to either use the shortened time period or even extend your time range so that each of your time intervals is an equal time interval. Note also that the data is mosaicked within each of the time intervals. So if you had, say, 2 Sentinel-2 acquisitions in a single time period, and your mosaicing was set as most recent, it would only take the data point from the most recent acquisition. But we'll see that in action in a second. So let's try and visualize this. So here in our example, we're looking at data for a time period of 31 days. So starting 1st of July 2024. And I want to put in an aggregation period of 7 days. So to do that, these have been sliced up on the red lines. So by default, the API split the time period into 5 slices. We've got 4 7-day slices, so up to 28 days. And then we've got this final 3-day time slice. So by default, it's discarded, as I said earlier, but we could also set the behavior to either shorten or extend this final time interval as we wish. Let's add some acquisitions into here. So in the request we're going to run here, we're going to use simple mosaicing. And we want to pick out the most recent image in each slice. As I mentioned earlier, you can also change this to least recent or least CC, the least cloud cover, if you want. And you can see here that we've got 4 acquisitions that we picked. In our first and third time interval, we actually have 2 acquisitions, but we always pick the most recent one and then discard the least recent in that time period. Okay, so hopefully that gives you a clearer idea of how the aggregation intervals work. Now let's look at Evalscripts with Stat API. So building an Evalscript with Stat API follows the same rules generally as Evalscripts with Processing API, but there are some specific things you need to note before you start building Evalscripts for Stat API. So firstly, the evaluate pixel function must, in addition to other outputs, always return a data mask output. This output defines which pixels are included or excluded from your calculations. So the default, and in addition, the default value of your sample type is always float 32. If you're asking why that is, by default processing API, it's unsigned integer 8. This would give you values of between 0 and 255. This is great for visualizing data, but this is not good for scientific analysis. So when we're dealing with spectral indexes such as NDVI, our values range from -1 to 1, but mostly within the sort of 0 to 1 range. And these are always going to be float values. So with decimal points, so say like 0.001 or 0.25, anything in between. And unsigned integers are not capable of producing these numbers. So we use float 32 because we're dealing with spectral indexes. In addition, the output bands parameter in the setup function can also be an array, and this makes it possible to specify custom names in the output bands, and also a different output data mask for different outputs as well. So maybe you wish to use a slightly different data mask for a different product. That's kind of up to you. So let's see how this works within an Evalscript. So here's the example I've got for you. We're calculating NDVI here. You can see here we use only band 4 and 8, which are the only bands required for the NDVI calculation. We can discard the rest of the Sentinel 2 bands, but also note that the data mask always has to be an input band within our Evalscript. We then define our outputs. We have 2 outputs here defined. We have our NDVI output, a 1-band image, and our data mask output as well, also a 1-band image. And that's our outputs defined. And then we look at our evaluate pixel function here. So we're applying the index function to, we are creating an index function here for generating NDVI. So we have the samples dot band 8 referring to the near infrared band, and samples band 4 referring to the red band in Sentinel 2. And we're calculating NDVI here. We then have a very simple return. We're returning index, our function up here, for NDVI, and our data mask as samples.datamask. So this is a really simple example. Let's have a look at how the output actually looks. So our output here, instead of maybe what we're more familiar with being a geotiff, we're looking here at a JSON file return. This is for a single time interval, but your JSON file could actually be several time intervals being returned at the same time. Just for simplicity, I've got one here. And you can see here that our interval was a 10-day interval from the 11th of October 2024 to the 21st. And in our outputs, we have our NDVI band here, which we were generating back in our Evalscript. And we've got some stats that have been created here for our field of interest. So the minimum, the maximum NDVI, we've got the mean. We also have the standard deviation. That's the standard deviation on the field level, rather than, say, the standard deviation over a time period. We also have the number of pixels as the sample count, and we also have a node data count. So this would have a higher number, say if we had some pixels that were masked out using the data mask, say if we had like a cloud over our field of interest, those pixels would be included in your no data count. So this just confirms to us that 100% of our pixels are valid for NDVI calculation. Okay. So next, we're going to look at how we can create some simple time series. I've got a few requests and a couple of different eval scripts to show you in these worked examples. So firstly, how to create an NDVI time series for a field of interest. We have our fields defined here. We're actually using a JSON file or GJSON file separately from the Jupyter notebook this was running. And then we define our geometry here. So we're using a geometry function baked into the Sentinel Hub Python wrapper. And we're calling the first geometry within our GeoJSON. So we actually have, I think it's 8 fields in our GeoJSON. But as we use in Python, we're using 0 to call out the first field. If we wanted to be, if we were interested in, say, the 5th one, we'd put 4, for instance, in that space. And then we have our request, as we saw earlier. We then have our aggregation. This is where we define our time intervals and aggregation intervals. We call our Evalscript. We're using the same Evalscript we looked at earlier. But this time we've got a longer time interval. So we're looking at data from the 1st of January 2023 all the way up to the 31st of December 2023. And we're looking for data at data points every 5 days. We then have a resolution here. This is set as 0.0001 because actually our area of interest in this instance was WGS 84. And the units for that are in degrees. So this corresponds to about 10 meters resolution. We then have our input data defined here as Sentinel-2. We're calling obviously the CDSE endpoints. This is important for you to get correct if you're working with Sentinel Hub APIs in CDSE. But this is documented in plenty of our examples for you. We then have our geometry defined as geometry, which was defined up here earlier, and our config, which is where we store our client ID and client secrets for working with the Sentinel Hub APIs. And then we can run this request. And after a little bit of manipulation with GeoPandas and Matplotlib, we can plot our data points on a nice line graph here with the mean and also the standard deviation as well. But you're probably looking at this and thinking that's quite a messy time series. Like, it doesn't look as good as, say, the one which we looked at in Copernicus browser earlier. And you'd be right. The reason why is because we're not filtering out cloudy acquisitions. So this is a really noisy graph because several of the data points will be pixels that are cloudy, and obviously the NDVI value of a cloud is going to be way off from what it should be when it's a field. So to counter this really simply, we have the exact same request here, except that all I've changed is added an additional argument here in the input data. So other args equals data filter, max cloud coverage 10. And 10 refers to the percentage. So we're only using images that had a cloud percentage. This is on a tile basis rather than your area of interest of below 10%. And you can see the result here is, yes, there are far fewer data points, but we have a much smoother time series to look at. We can actually see a peak in spring, and then it obviously dips back down in the summer before maybe an autumn crop being planted again in early autumn and rising again. You can see here that actually the time period ends quite early, and that's an indicator that there was no images that were below 10% cloudy after that particular data point. So it's actually a shorter time period than the previous time series. Okay, so In addition to that, though, you can actually plot multiple vegetation indices on the same plot and actually request them in the same request as well. So in this example, we've just changed the Evalscript. We're now calling band 3 as well. And as well as NDVI, we're calculating NDWI. And you can see here in our evaluate pixel function, we've got the same as we had previously, except we're using a baked-in index function, which is part of the Evalscript functionalities, and calculating NDVI, NDWI, and of course we have our data mask again. And the actual request itself, exactly the same as before. And again, using some GeoPandas and Matplotlib manipulation, we can then plot NDVI and NDWI onto the same plot and see how they correspond to each other. Okay, and then you can take it a step further. You can start comparing different crop types. Like maybe you have the knowledge of a field's particular crop type and want to compare it to different fields. So here we have an example from Latvia. I have 3 groups of crops that I know were planted that particular year. I have winter wheat, winter rape, and field beans. And wheat and rape are quite similar in their profiles, as we can see, with the yellow and the green data points. I should add, we have 6 fields for the wheat, 5 for the rape, and 4 for the beans. So we can actually see the standard deviation of each field, but also the overall data set as well. And we can see that they have quite similar profiles, the wheat and the rape, but get harvested at similar kind of times. But there's this interesting like trough, like here going on with the rape, and that's in about May. And that's actually associated with the yellowing of the crop in May as the rapeseed flowers. When the crop turns yellow, it actually reduces the NDVI response, which is kind of interesting. And then we also have beans, which is quite a different crop type. We can see the NDVI values stay much lower for much deeper into the growing season, but then shoots up quite late on in May, and then is harvested at quite a similar time as well. So to scale this up even further, I want to briefly introduce you to the batch statistical API. So this enables you to request statistics, similar to what we've just done, but for multiple polygons at once, and for even longer aggregations. So a typical use case for this might be, it could be related to the Common Agricultural Policy, but maybe as a country, you wish to calculate statistics for your whole country. You'll have not even thousands of fields, you'll have tens of thousands of fields to analyze. And the batch API is the way to do this quickly and on scale. So similar to the batch processing API, this is an asynchronous REST service. And this means that your data is not immediately returned to you in the response, like say to be used in Jupyter Notebook, but the JSON files are delivered to object storage. In the context of CDSE, this would be provided through CreaDS as S3 storage. So for that, if you're interested, I would encourage you to reach out to us via our support email. Okay, finally, I just want to introduce you to some other plots you can create. So firstly, you can very easily generate spectral signature plots. In this example, we're looking at 3 common land cover types. We've got some water, some forest, and some urban fabric and grassland. And we can create our areas of interest and then compare the spectral response like so. You could change this to a box plot as well. So what this enables you to do is actually start looking at how heterogeneous or homogeneous a land cover type is. So very quickly analysing this, you can see that water and forest are quite homogeneous land cover types. Water is obviously quite dark, has a very low NDVI value, whereas forest has a much higher NDVI value, so above 0.8 generally. And then you can see here, urban fabric, very heterogeneous because it's obviously encompassing densely populated urban areas, but also the sort of suburbia that contains gardens, trees. So actually its NDVI values can fluctuate quite a lot. And you also have grassland, which is generally has higher NDVI values, but is a little bit more heterogeneous than, say, forest. We also have scatter graphs. Again, it's a good way of seeing how different land cover types are grouped. We're comparing band 4, so the red band, and band 8 on the X and the Y axes respectively. And we can see how dark and homogeneous water is right down in the bottom left of the graph. And then we can see the 3 other land cover types. There's quite a lot of mixing, maybe in the center of that kind of triangle that's been created. But if you were generating, say, a rule-based land cover classification, this will give you a good basis for some of the rules that you could use to separate out your land cover types. Okay, so finally, I just want to show you where you can find some additional documentation and also the worked examples that I've shown you today. So I'm just going to move over to my browser. And firstly, let's take a look at the CDSE documentation page here. So you can go to APIs, Sentinel Hub Statistical API, and here you'll be able to read into the API's features in more detail. We also have some examples here as well, which you can click on this page and get taken to some additional examples for Stat API. In addition, we have examples on the Sentinel Hub Python package website as well. Again, you can navigate to the Copernicus database ecosystem examples. We have some specifically for statistical API, and you can use these to help you with your own work. But lastly, the examples which I think probably most useful to everyone are found in our notebooks samples repository here. So to visit this, you can go to github.com/EUCDSE/notebook samples. You can navigate to the Sentinel Hub folder. And within here, we have 2 notebooks that are specific to Stat API. So firstly, we have one for the visualization of basic time series. You can scroll down and see how you build your request. See then how you can actually manipulate the API request into a pandas data frame, and then plot a matplotlib plot like so. And you can see a few more examples than what I showed you today as well. And then finally, behind the controls, also have the more advanced Stat API visualizations as well. So in here, we have how you can create your fields of interest or your areas of interest for your land cover types. So in this example, we're using areas of interest around Zurich. And then how you can actually generate your more advanced visualizations, such as your spectral response graph, like so, and then how you can style it to reflect your different land cover types. Yeah, so we also have the box plots and how you can create basic scatter plots, but also add in your multiple land cover types. Okay, so I'll go back to the presentation, and we also have some additional useful links for you. So as always, it's worth exploring the data in Copernicus browser first. If you're not already subscribed, please go ahead and subscribe to our regular newsletter. Check out the gallery on dataspace.copernicus.eu. And if you do have any questions, you can reach out to us and the community at the forum.dataspace.copernicus.eu, and we'll be happy to help. And I'll pass back to Sabina.
Thank you, Will. It seems like we don't have any questions. Oh, sorry, we have. Does the statistical API run on the fly?
If you're referring to whether it's asynchronous, also it's synchronous, yes. So when you run your request, you can either save the response as a JSON file and then manipulate it offline, or you can actually run it from the memory in your Jupyter notebook and then generate your graphs from there. But yeah, it's an instant delivery of the stats to your computer.
We have another question. What are the key differences of Sentinel Hub and to OpenEO API?
Good question. As a Sentinel Hub expert, I'm probably not the best to answer that. But both will give you access to the same data. It's just different ways of actually implementing it. So there are pros and cons to both the API approaches. But I think we could share that in a newsletter. I believe there is an article out there that you can refer to.
Will Andras just let us know that there is a blog post about it. So he just shared it in the chat, and you can check it there for more details.
Perfect. Thank you, Sabina.
Then we have another question. Is it possible to use the statistical API mean SD histograms for SAR images like Sentinel-1?
Yes, yeah. So yes, all the examples I've shown today have been Sentinel-2, but you can use other data collections that are part of the Sentinel Hub data collections in CDSE. So that includes Sentinel-1, GRD data. That's the only product from Sentinel-1 we offer in Sentinel Hub. We also have Sentinel-3, so the OLSI and SLSTR sensor, Sentinel-5P, as well as some Copernicus land monitoring service datasets as well. So you're able to use the Stat API on any Sentinel Hub data collection you wish.
Will, there is another question regarding the batch processing. How long does it take to process? As you mentioned, it is asynchronous.
Yeah, that will depend on multiple factors, like how many fields of interest you have, the time period you're using, the complexity of the analysis, but also the traffic. So you're obviously not going to be you might not be the only user of that API. And jobs do get queued up sometimes. So I can't give an exact answer, but you're looking at normally probably about an hour.
If there is no other questions, okay. So in that case, I would like to thank you for joining today's webinar. We hope it gave you useful insights into the Sentinel Hub Statistical API. If you have further questions, as Will already mentioned, you can freely use to continue the discussion on the CDSE forum. We would also like to use this opportunity to invite you for our next webinar, which will be held on October 14th, and it will focus on an introduction to working with custom scripts with the Sentinel Hub APIs in the CDSE. For that, I invite you to follow our social media channels where we will post the official announcement and further updates. We look forward to seeing you there, and thank you for now.